In section 3.4, Eigenvalues and Eigenvectors, you will learn what eigenvectors and eigenvalues are, and also how to calculate them for a given matrix. Let's start with an example. Consider this matrix A equals 11, 3 on the first column and minus 36, minus 10 on the second column. And I'm going to multiply A with two vectors. The first vector I'm going to multiply by is 4, 1. So let's just write down A again and our vector, and then multiply. To get the first entry, you multiply the corresponding entries on the first row of A with your column vectors. So 11 times 4 minus 36 times 1, you get 8. And then for the second entry, you multiply 3 times 4 plus minus 10 times 1, and then you get 2. But the important thing here is that this vector, 8, 2, is 2 times what we started with. So we plugged in the vector 4, 1, we multiplied by a matrix, but what happened was we just multiplied by a number, 2. Let's try another vector. Now I want to multiply by 3, 1. And here's the multiplication written out with the matrix and the vector. To get the first entry, you would do 11 times 3 minus 36 times 1. And then for the second entry, you would do 3 times 3 plus minus 10 times 1. You get minus 1. And then you should notice that this new vector, minus 3 minus 1, is actually just minus 1 times what we started with. Minus 1 times 3, 1. Okay. So this sort of thing, this phenomenon, has a name. And that's what we're going to go over here in this definition. Let A be an n by n matrix, like the 2 by 2 matrix in the example. A scalar lambda is called an eigenvalue of A if there is some non-zero vector x such that A times x is equal to lambda times x. So just like in the example, we found vectors where we could get a multiplication by 2 or a minus 1. This can happen for any matrix, and we call the scalars eigenvalues. And then the vectors also get a name. The vector x is called an eigenvector of A corresponding to lambda. So x is the same vector here in this equation. It's what we multiply by the matrix A. So now that we've encountered this idea, something that we might want to do if we're given some matrix is actually find the eigenvalues and eigenvectors for a matrix. So in the example, I just gave you vectors, and they happened to be eigenvectors. But what if we're just given a matrix? How could we find eigenvectors and eigenvalues? Let's think through what that actually means, what we would be trying to do. And what we would be trying to do is to find scalars lambda and corresponding vectors x that satisfy this equation here. So we have our matrix times the vector, and that's equal to the scalar lambda times the vector. And we always want to have a square matrix, an n by n matrix. And then I've just written in these names. So the vector is an eigenvector, and the number is an eigenvalue. Okay, so this is our starting point. Let's rearrange a little bit. So the first thing I want to do is move everything to one side of the equation, and nothing changes. So ax is equal to lambda x if and only if ax minus lambda x is equal to 0. So I'll just move this to the left. What I want to do eventually is factor out the vector x. But in order to do that, I have to have two matrices being multiplied by x. And right now I just have a scalar. So what I'm going to do is rewrite lambda x as lambda times the identity matrix times x. So putting in the identity matrix doesn't really change anything in our equation, but it will let us do this factoring. So we take the a minus lambda in and factor it out and leave the vector here on the right. And we don't do anything with the 0 this whole time. So what we've done is rearranged this to look like a homogeneous system of equations. And something that we learned in the previous section is that a system of equations for a square matrix, so n variables and n unknowns, this has a unique solution if the determinant of the matrix is not 0. And something I should point out before we get any further is that this homogeneous system always has at least one solution, and that's the 0 vector, because if we plug in the 0 vector here and multiply by anything, it doesn't matter what's here. We're always going to get 0. So something times 0 is equal to 0. But if this determinant is 0, then this determinant is non-zero, then that solution is unique, that x equals 0 solution. And the other thing that we learned in the previous section is that this equation has many solutions if the determinant is equal to 0. So this is what we're going to be looking for, because we want to find non-zero solutions to this equation. That's when we know we're going to have an eigenvalue. So that's our conclusion. The scalar lambda is an eigenvalue of the matrix A if this determinant, A minus lambda in, is equal to 0. Let's give a few of these things names. A is still going to be a square matrix, an n by n matrix. This determinant that I've been talking about, A minus lambda in, has a special name. It's called the characteristic polynomial. The idea here is when you calculate this determinant, you're going to end up with an expression with lambda as a variable. You're actually going to end up with a polynomial. And then the equation setting the determinant equal to 0 is what's called the characteristic equation of A. So to compute eigenvalues and find the corresponding eigenvectors, we have a strategy after this discussion. So the first thing we'll have to do for a given matrix A is to solve the characteristic equation. So you'll have to compute this determinant, set it equal to 0, and then solve for lambda. And then once you've found your eigenvalues, your values of lambda from this equation, you'll have to substitute those values back in to the matrix equation, A minus lambda in times the vector x equals 0, and then use Gauss-Jordan elimination, row reduction, to solve for the eigenvectors, the vectors x. Okay. So that discussion was mostly theoretical up till then. Let's try to make it more concrete by working through an example. We're going to look at the same matrix that we started with, and I already told you two eigenvalues and two eigenvectors of this matrix. So we have an idea what the answer to this should look like. when we're trying to find the eigenvalues and the corresponding eigenvectors. Essentially what we're going to be doing here is seeing where those vectors and eigenvalues came from. So we'll work through our strategy first by solving the characteristic equation. So let's work out that determinant, a minus lambda, and since we have a 2 by 2, we'll have an I2 matrix. So here's A minus lambda, and there's the 2 by 2 identity matrix. And in order to combine this into a single matrix, you'll have to multiply through by lambda here on the identity matrix. So you get lambdas on the diagonal, zeros everywhere else. And then you do the subtraction. So 11 minus lambda, and then minus 10 minus lambda, and then nothing changes in the other two entries. And then, since we now have a 2 by 2 matrix, a 2 by 2 determinant, we take the product of the diagonal entries and subtract. So that's 11 minus lambda times minus 10 minus lambda, and then minus negative 36 times 3. What you'll want to do is distribute through here, multiply there, and combine it into a nicer looking polynomial, and you get this much simpler looking polynomial, lambda squared minus lambda minus 2. So that's the characteristic polynomial. Remember, the characteristic equation is where we set the characteristic polynomial equal to 0. And this one we can solve by factoring. This is equal to lambda minus 2 times lambda plus 1. And since this is equal to 0, we know that lambda has to be equal to 2, or lambda has to be equal to minus 1. So those are the two eigenvalues for this matrix, and you should remember that these are the same two eigenvalues that we saw in the example that started off this section. So moving on to step 2 of our strategy, we're going to find the eigenvectors for lambda equals 2. So what this means is we're trying to find the vectors that solve this equation, that are solutions to this equation. So we'll have to set this up in an augmented matrix in order to do row reduction. And just as a quick reminder, we've already thought about what A minus lambda I2 is, and that's just this guy, where we've subtracted the number, the eigenvalue, from the diagonal elements. So when I'm solving this equation, I don't have to work through this math again. I know that it's going to be the original matrix minus this eigenvalue, and the original matrix is here. So my diagonal entries are going to be 9 and minus 12. There. And then the off-diagonal entries are going to stay the same. And this is a homogeneous system, so I've just added a column of zeros for completion. Now we row reduce. You'll want to divide through by 9 to make this into a 1. And then use that 1 to cancel the 3. So multiply row 1 by 3 and subtract from row 2. And finally you get this. We have a row of zeros, and then the first row translates into x1 minus 4x2 is equal to 0. So to write out the solution, if x is some unknown vector, x1, x2, then we know that x1 has to be equal to 4x2, so substitute that in. And now there's a common factor of x2 that we can factor out, and then we can see that all solutions to this equation are scalar multiples of this vector 4, 1. And this is the vector that I gave you in the example to lead off the section. So one thing that you might want to think about or really remember from a while back, is that when you have scalar multiples of a vector, you're looking at linear combinations of a vector. That means that this is actually a subspace. All linear combinations of a single vector is a subspace of R2. So we have the eigenvectors for lambda equals 2. Now we'll need the eigenvectors for lambda equals minus 1. So we're going to solve the same kind of equation, but minus 1 has been plugged in for the eigenvalue. So we're going to be subtracting negative 1 from the diagonal entries of A. That gives us a 12 and a minus 9 on the diagonal. The other entries are the same. Then you row reduce to solve the equation. So divide 3 by 12 on the first row, and then use that 1 to eliminate the 3 by subtracting 3 times row 1 from row 2. And then you get this final matrix in reduced row echelon form, and the first row translates to x1 minus 3x2 equals 0, which helps us when we write out the solution. So our unknown vector is x1, x2, but we know that x1 is equal to 3x2. Then we factor out the x2, and we see that the solutions to our equation are scalar multiples of the vector 3, 1. And this is the vector that I gave you in the example that corresponds to this eigenvalue, minus 1. So once again, we have scalar multiples, linear combinations of a vector. That means that this solution set is going to form a subspace